All right, so last time we have discussed the different properties of extrinsic semiconductors. No? So semiconductors that are subjected to impurities, and yung process na yun ay tawag natin na doping. Kaya natin dinodope or kaya natin hinahaluan ng mga extenders, kumbaga itong mga intrinsic semiconductors, is para gumanda ang kanilang conductivity. Okay? So the more doped a semiconductor material is, the more it is being conductive. So mas maganda siya. No? Kasi pag binayas natin siya, pag pinorward bias natin, mas lalo siya magko-conduct ng electricity or ng kuryente. No? So in the conduct of analyzing diode and diode circuits, meron tayong mga ginagamit na mga diode models na tinatawag. When we say diode models, these are used to represent or approximate the characteristics of the diode. So ang ginagawa kasi natin sa computation or sa calculation, we just approximate the characteristics of that semiconductor material, kagaya ng diode. No? Kasi we cannot directly measure, for example, yung impedance. No? Yung impedance, nagbabago-bago yan. Impedance, which also means resistance. I don't know kung na-discuss kayo, but siguro papahapyawan ko later on, no? Yung impedance na tinatawag. And also yung kuryente na dumadaloy sa kanya. No? There's no direct way of actually measuring or calculating the actual value. No? Kasi pa pwedeng magbago-bago. That's why ang ginagawa natin in analysis, no? Nagkakaroon tayo ng approximation. Yung approximation na yon can be carried out by using diode models. So meron tayong mga gagamitin na diode models. Ang pinakauna is yung tinatawag na ideal diode equivalent model, or just to simply state it, it's called the ideal diode. So alam natin na ito ang schematic symbol ng diode. So we have again yung parang puwetan ng diode natin. It's the P-type material, which is called the anode, and this is the N-type material, yung merong guhit. No? This is called the cathode. So again, letter K yung ginagamit natin for the cathode. So what if we forward bias the ideal diode? So ideal diode muna ang usapan natin ngayon. And later on, we will have the practical diode. We'll have the different models. So what if we forward bias the diode? When we say forward bias, the anode must be positive with respect to the cathode. Yun yung unang isa sa mga kondisyon natin. Pangalawa, kailangan ay abutin niya ang threshold voltage. So kailangan pasok dun sa dalawa. Okay? The ideal diode, pag positive ang anode with respect to the cathode, or pag negative ang cathode with respect to the anode, automatic siya ay naka-forward bias. Yun ang tatandaan natin for the ideal diode. Automatic siya. So this is automatic. If the anode is positive with respect to the cathode and vice versa, matik yan, naka-forward bias. Yan ay for ideal diode only. Okay, bakit? Remember, meron tayong different values ng threshold voltage. No? For silicon, we have 0.7. For germanium, we have 0.3. For gas, we have 1.2. And depende sa kanyang construction at kulay, magkakaroon siya ng pagkakaiba sa threshold voltage. Pagdating natin sa optoelectronics, didiscuss natin yan. But for the ideal diode, hindi mo na kinakailangan yung mga 0.7 na yan, yung 0.3, yung 1.2 na yan. Hindi na kailangan. Matik na. Basta positive ang anode with respect to the cathode, forward bias na agad ang ideal diode. Okay? So kapag forward bias siya, ano ang kanyang equivalent? Okay? So tatandaan natin, if it is an ideal diode, ang equivalent niya kapag siya ay naka-forward bias, it is equivalent to a closed switch. It is equivalent to a closed switch. Ang resistance or impedance ng isang closed switch ay equal sa 0 ohm. Okay? So parang wire na lang yan eh. So kapag kukunin natin ang resistance ng isang wire is approximately equal to 0. Okay? Yan ang equivalent ng ideal diode kapag naka-forward bias. Closed switch. Okay. What if we reverse bias the diode? If we reverse bias the diode, it means that the anode is negative. So nakalagay dyan, with respect to the cathode. So nagkabaliktad lang yung kanilang in-apply na bias. Okay? ano ang equivalent circuit ng ideal diode if it is reverse biased? Ito ang equivalent niya ngayon. This is equivalent to an open circuit. Okay? Or an open switch. No? So ibig sabihin niyan, walang daanan ng kuryente. This is for ideal diode. Okay? But sometimes in the practical diode na tinatawag, sometimes we consider also the open circuit. So this may be applicable for ideal and the practical diodes. Okay? So matik yan, no? Kapag ka reverse bias, pwede nating i-assume na open circuit siya. So walang dumadaan na kuryente, but yung practical diode in reality, di ba, may dumadaang kuryente sa diode kapag naka-reverse bias, but it is very, very small. Ang tawag doon ay I sub S, or the leakage current, or the reverse saturation current, which is in the range of nanoamperes or picoamperes, which is approximately equal to 0. So sa sobrang liit, no? Almost 0 na siya. Kaya ang equivalent niya ay open circuit. So yun tatandaan natin. Kasi this is the basic equivalent model or circuit para sa isang diode. Most of the times, no, kapag gusto nating mapadali yung analysis natin, ang ginagamit natin ay ideal diode. So pagdating natin sa wave shaping circuits, gagawa ako ng analysis, isa pang ideal diode at isa isa para sa practical diode. Okay? So yan, tatandaan niyo, the ideal diode equivalent circuit. But before we proceed to the practical diode, kasi sa practical diode, meron tayong mga models na ginagamit. We have the piecewise linear, we have the simplified equivalent circuit, and we have the ideal diode. So unahin ko muna itong characteristic curve ng ideal diode. Sa ideal diode, ang kanyang characteristic curve, remember meron tayong sinusundan na Cartesian coordinate system. No? We have the x-axis, it represents the diode voltage, positive VD para dun sa positive x, and negative VD of course para sa negative x. This represents the forward bias region, yung nasa kanan, and this represents the reverse bias region, yung nasa kaliwa natin. So for the ideal diode, ganito nangyayari. Matik, kapag positive ang anode with respect to the cathode, tataas agad yung kuryente. Dire-diretso. Okay, so this is I sub D in milliamperes. Hindi na natin kinakailangang hintayin yung 0.7. While if it is reverse bias, almost talaga walang kuryenteng dumadaan. So this is the characteristic curve of an ideal diode. Okay? Wherein, yung characteristic curve ng practical diode, so halimbawa 0.7, di ba? Hihintayin niya pa yung 0.7 bago siya mag-conduct. Okay? And then meron siyang Zener region or avalanche region. Okay? So yung kulay green, that is the characteristic curve of the practical diode, and yung kulay pula, yan yung characteristic curve ng ideal diode. So let's just write this down dito. This is the characteristic curve of a practical diode. Practical diode meaning this generally represents the characteristic curve ng mga diodes available in the market. So halimbawa, lagi kong binibigay na example sa inyo, 4001 tsaka yung 4148 kasi that's the most commonly used. So, posibleng ganyan yung maging itsura ng kanilang characteristic curve. But hindi sila eksaktong pareho. Ito yung sinasabi ko sa inyo na hindi natin direktang ma-measure or makakalculate yung ating value ng impedance or resistance. No, we just do approximations. So, magkakaroon tayo ng approximate models and general models kagaya nito. Okay? So, yun yung tinatawag na ideal diode model. Okay, before we proceed to the other equivalent models, punta muna tayo sa resistance levels. Ano ba yung resistance levels na yun? Resistance is, di ba sabi ko sa inyo before, we discussed the fundamental electrical properties or quantities rather, no? Resistance, kuryente, voltahe, power, so on and so forth. Pag sinabi nating resistance, this is the opposition to the flow of charges. So pag mas mataas ang resistance, mababa ang kuryente. Pag mababa ang resistance, mataas ang kuryente. Okay? But what is impedance? Ito yung sinasabi ko sa inyo kanina. what is impedance? So I hope na-discuss ko sa inyo pero papahapyawan ko siya dito. No? What is impedance? You can think of impedance as resistance. It's another term for resistance pero impedance is represented by letter Z. Okay? Ano yung mga components niya? We have R plus minus JX. Naging complex number. So hindi ko alam kung naalala niyo pa yung complex number na yan. No? So this represents impedance. Impedance is composed of the resistive component, purely resistive, meaning fix yung kanyang resistance. Okay? And we have letter X, this is the reactive component. Or this is what we call the reactance. Ano may reactance na yun? Reactance is the resistance being offered by capacitors and inductors. Aba, may resistance pala yung capacitors, may resistance din pala yung inductors. Ang tawag doon ay reactance. So kapag pinagsama natin yung purely resistive component, which is this one, purely resistive, tsaka yung reactance or reactive component, pag pinagsama natin yan, yan ay magiging impedance. But you can also think of resistance as impedance, the same with reactance. No? So, kahit mag-zero out yung, let's say, yung purely resistive component at ang matitira ay reactive component, pwede pa rin natin siyang tawagin as impedance. Okay, so huwag kayong malilito doon. Kasi yung impedance is a general term used for purely resistive and purely reactive components. Kasi ang resistance or reactance ng mga capacitors and inductors, nagbabago-bago yan. Ang reactance, this is frequency dependent. Ano ibig sabihin nun? Yung resistance niya, nagbabago depende sa frequency. Okay? So meron tayong formulang ginagamit dyan before we go to the resistance levels. We have what we call X sub L. This is what we call the inductive reactance. Yan yung resistance na ino-offer ng mga inductor. So, titignan mo natin, baka i-discuss ito sa inyo sa circuits. Saka po na lang siya i-discuss kung hindi siya may discuss. We have, this is equal to 2 pi FL. So 2 times pi times the frequency in hertz. So this should be in hertz. Anong unit ng inductance? This is in henries. Okay? So kailangan naka-base unit sila para ang sagot natin dito ay naka-ohms. Yung isa naman, yung X sub C, this is what we call the capacitive reactance. So this is equal to 1 over 2 pi FC. So F should be in hertz and capacitance should be in farads. So kailangan pag nagko-compute tayo ng reactance, whether it is inductive or capacitive, ay naka-base units tayo ng hertz, henries para sa inductor, at farads para sa capacitance. So makukuha natin pareho dito dapat ay naka-ohms. Frequency may change kasi if we subject the circuit to an AC waveform, so let's say it's 1,000 hertz or 1 kilohertz, tapos nag-increase siya, nag-increase yung frequency natin, let's say naging 1.5 kilohertz, magbabago na ulit yung kanyang reactance. That's why it is governed by these equations. Habang nagbabago yung frequency, nagbabago rin yung ating reactance. So they are frequency dependent. While henries, rather inductance, tsaka yung capacitance, they are constant. So constant to pareho. Of course, the same with 2 pi. Constant naman yung 2 pi na yan. Okay, so that's the nature of impedance. So hindi ko na masyadong i-discuss in detail kasi I think i-discuss naman to pagdating sa circuits. No? Ayoko lang magkaroon sa inyo ng confusion pag binabanggit kong impedance, baka bago sa bago nyo napakinggan itong term na tong impedance na to, you can think of impedance as reactance or resistance. Okay? So, we now go to what we call the DC levels. DC levels ng ating diode. Yung DC level natin is part of the resistance levels. Resistance levels, ano daw ba ang resistance or impedance? Okay, malilito What will be the impedance of the diode when it's subjected to different voltage levels. Kung DC ang in-apply natin, ano yung corresponding na impedance? Kung AC ang in-apply natin, ano yung corresponding na impedance din? Okay? At least sabi ko sa inyo kanina, no, nagbabago-bago ang resistance or impedance ng mga diode. Okay? So for the first one, we have here a silicon diode. Yan. So alam natin ang silicon diode around 0.7, magsisimula na siya mag-conduct. So let's say this is around 0.7. Ano napapansin natin? No? At 0.7, hindi naman siya talaga diretsong pataas. So meron pa siyang konting pakurba. Medyo nag-increase pa siya paunti-unti. So kung titignan nga natin dito, around 0.8 volts pa. Pero bakit 0.7 ang ginagamit natin as the threshold voltage? Again, 0.7 is the average or the nominal threshold voltage ng silicon. Ibig sabihin, generally speaking, pagdating ng 0.7 ay magsisimula na siyang mag-conduct. Yun ang property ng silicon. But in reality, pwede pa siyang umabot ng 0.8, 0.9, even 1 volt. Depende dun sa diode model. Ito yung hindi nadi-discuss lagi, no? Pagdating sa electronics. Pag sinabing 0.7 silicon, isipin na ng estudyante ay puro 0.7 na lang yan. Fix na 0.7. Hindi. Depende yan sa model ng diode. No? So, this is just a general value, yung 0.7 na yan. So, tatandaan. Hindi lang fix sa 0.7. Okay? So, for example, we have here a specific point dun sa ating characteristic curve. Diba this is called the characteristic curve? So, we are relating yung kuryente versus the voltahe. So, we have the kuryente versus the voltahe ng ating diode. So, diode current, this is in DC, and the diode voltage also is in DC. Okay. What if we selected a certain point doon sa ating characteristic curve, kagaya nitong point na to? Okay? Ang tawag doon sa point na yon, since fixed siya, no? So that is what we call the Q point. Q stands for quiescent. Ibig sabihin yan, still or unvarying. Or pwede nating isipin na fixed. Fixed point siya doon sa ating characteristic curve. Paano natin nalalaman yung Q point? Meron tayong tinatawag na load line analysis. Load line analysis, kagaya ng sinabi ko sa inyo last meeting I think, no? This is the property of the diode. And then magpo-project tayo ng, let's say, isang diretsong line. This is the property of the circuit. So depende ito, no, dun sa circuit na gagamitin natin. Anyway, gagawin natin yan pagdating natin sa DC load line analysis. Don't worry. No, so, for example, nag-DC load line analysis tayo. Tapos yung intersection niya, nakuha natin na itong point na yan. So, we're going to project it to the left. Tapos, nung pinoject natin siya to the left, nalaman natin na ang value ng kuryente, corresponding na kuryente niya is 20 milliamperes. Pinoject natin pababa, okay? Nalaman natin na ang corresponding na voltahe niya ay 0.8 volts. So, ibig sabihin, yung point na yon, merong combination ng X and Y values. So, lagay natin, no? X and Y values. Ano yung X value natin? The X value indicates your diode voltage and the Y value indicates your diode current. So, pares yan. Okay? What if meron tayong ibang circuit tapos may corresponding point dito determined by the load line? So, magbabago na ngayon yung XY na pares natin. So, this is roughly, let's say, around 10 volts and let's say this is roughly around 10 milliamperes and this is roughly around 0.7 volts. So, ibig sabihin, yung XY values na yun or V sub D and I sub D values na yun, pwedeng magbago depende sa Q point. Q point is defined by the load line. Load line is the property of your circuit. Okay? So, may nakuha tayong XY values, di ba? So, ilagay natin siya into equation form. Alam natin, ng Ohm's law is V is equal to I times R. So, voltage is equal to the current times the resistance. So, pwede natin i-replace yung mga subscripts nila. So, we have V, lalagyan natin subscript na D to define that this is the diode voltage. V sub D. Take note, capital yung subscript ko, ha? Mamaya magiging small caps na yan. Okay? Kasi ang capital subscript, tsaka the same with the variable, kasi pwede tayong magkaroon ng maliit na variable, for example, na V. Yung capital letters, they indicate DC values. So, sulat natin para hindi makalimutan. No? Capital letters, they indicate DC values. And of course, yung small caps or small letters, they indicate AC values. Natandaan niyo yan. So, ibig sabihin, ang kinukuha natin dito, DC voltage, and meron tayong DC current, kasi I sub D na capital, and we have R. Ano kayang subscript ng R natin? DC ang voltahe mo, DC ang resistance mo. Siyempre, yung R mo, DC rin. Okay, so we can represent that by R sub D. R sub D can be solved by using V sub D divided by I sub D. Eh di ba may value ka ng V sub D? May value ka rin ng I sub D. V sub D tsaka yung I sub D, fixed points in your characteristic curve defined by the loop line. Okay? Therefore, RD will also be a fixed value or a Q point value. Hindi siya nagbabago kasi fixed yung VD mo, fixed din yung ID mo, edi fixed din yung value ng RD mo. That's why this is called DC resistance. The other term for DC resistance is static resistance. Okay? So kailan tayo nagkakaroon ng DC or static resistance sa diode? Nagkakaroon tayo ng DC or static resistance sa diode if and only if pag nag-a-apply tayo ng DC voltage sa ating diode. Hindi ka pwede magkaroon ng AC value kung DC voltage ang ina-apply mo. So this is the resistance or the impedance if a DC voltage is applied to the diode. So DC resistance. Yun yung isang klase ng resistance level ng diode. So let's solve for this one kasi we have values dito. I have an example here. So solve for the DC value or the DC resistance of the given characteristic curve. So ito makita natin, no, meron tayong 20 milliamperes defined by this point and we have 0.8 volts. So ang gagawin natin to solve for that, napakadali lang. R sub D is equal to V sub D over I sub D. So direct substitution lang. We have diode voltage of 0.8 volts divided by 20 milliamperes. Okay? So, ilan to? Calculate natin. Papakita ko sa inyo yung calculation. So, we have 0.8 divided by 20. So, yan na 0.04. This is 0.04. Ang unit nito, resistance siya. So, anong unit ng resistance? Ohms. Pero ang dinivide natin, volts per milliamperes. Matik, kapag nag-divide tayo ng volts and milliamperes, kilo ohms agad ang unit niyan. If we're going to express this in terms of ohms, multiply mo lang ng 1,000. So, 1, 2, 3. So, this is equal to 40 ohms. So, ibig sabihin, nung meron daw tayong voltahe na 0.8 dun sa diode at dumadaan ng 20 milliamperes sa kanya, ang resistance niya ay 40 ohms. Okay, so kung papansin nyo, mababa lang, no? Mababa lang yung resistance natin kasi masasabi natin mataas ang resistance if it is in the range of kilo ohms. Okay? Next, what if we want to solve for the resistance at this point? So itong kaninang ginawa ko, isang 10 milliamperes at ang corresponding na voltahe niya is let's say 0.7. So kunin natin yung resistance at that point kasi we have the first point and we have the second point. So maaring na iba yung circuit na ginamit mo, kaya na iba yung Q point. Okay? So we have 10 milli and 0.8 volts. So we have R sub D is equal to 0.7 volts divided by 10 milliamperes. So this is equal to 0.07 kilo ohms. Kasi volts over milli, matic, kilo ohms. Ilan ang kanyang, kung i-convert mo sa ohms, ilan yan? Multiply by 1,000. Ganun kasimple. 1, 2, 3. So 70 ohms. So nakikita nyo, isa 40 ohms, isa 70 ohms. Ibig sabihin, pwede magbago yung DC resistance mo depende sa Q point. Okay? Depende sa Q point. Okay? Pero at that specific point, let's say at this point, ang na-compute natin dito, di ba, 40 ohms. Tapos kinuha mo ulit. Hindi pwedeng maging 50 ohms yan, hindi pwedeng maging 70 ohms. Bakit? Kasi fix nga siya sa point na yan eh. Pwede siya maging 50 ohms or 70 ohms kung pipili tayo ng ibang point doon sa ating characteristic curve. Okay? So I hope you understood what I mean by DC or static resistance. It is the resistance sa diode or impedance sa diode kapag nag-a-apply tayo ng DC voltage sa isang diode. Okay. May DC resistance tayo. Of course, meron tayong AC resistance. Pero ang AC resistance, may dalawang klase yan. No? Kailan ba tayo nagkakaroon ng AC resistance? Yun ang tanong. Sa DC resistance, nag-apply ng DC voltage, may DC resistance. Sa AC resistance, pag nag-apply naman tayo ng AC voltage or AC input sa isang diode, doon lang tayo magkakaroon ng AC resistance. Okay? So, pwede siyang magbago. But what we're taking here is what we call the dynamic resistance and the average AC. So, dalawa tong example ko. Ito, ang kukunin natin dito is yung tinatawag na AC dynamic resistance. Dynamic resistance. Okay? For this one, this is governed by what we call Shockley's equation. Mamaya papakita ko sa inyo yung Shockley's equation na tinatawag. And also yung Shockley's equation na yun, gagamitin natin yung pagdating natin sa transistors, pagdating natin sa pagko-compute ng level ng emitter current. So listen carefully kasi yung concept dito is not only applicable to diodes but also applicable to BJTs, bipolar junction transistors. Okay? So dito sa pangalawang example, as you notice here, no? Ay di pala nakadrawing yung yung input. So let's say may input ka. Let's say an AC input. Yung gitna ng sine wave mo, for example, yan, di ba zero yan? So that determines your Q point. Pero above and below your Q point, pwedeng maglaro yung waveform. So pwedeng tumaas, so above, pwedeng bumaba or below, which represents your AC signal. So this is the AC signal for current. Of course, nagbabago yung ating kuryente, mayroon din corresponding na pagbabago sa voltahe. So let's say in this example, naglalaro yung kuryente natin sa pagitan ng 20 milliamperes hanggang 30 milliamperes. Ang gitna niya ay 25. So ang peak current niya, ano kaya yung peak current niya dito? This is 5 milliamperes. This is also 5 milliamperes. If we're going to take it in the negative direction, it's negative 5. Okay? So kapag kinuha natin peak-to-peak current, that's just equal to 30 minus 20 is equal to 10 milliamperes. Or pwede rin naman twice the value of the absolute value. So we have 2 times absolute value of the peak current. This is equal to 10 milliamperes. Pwede rin naman to. 30 minus 20 is equal to 10 milliamperes. So it's the same. So either of those technique na ginamit ko or pag-compute na ginamit ko, makukuha niyo pa rin yung peak-peak. Okay. Dahil nagbabago yung kuryente natin, of course, meron siyang corresponding na pagbabago sa voltahe. But at this point, medyo maliit yung change niya. No? So, izo-zoom ko siya. So, tignan natin kung makikita niyo to. Yan. So, nagbago yung kuryente natin, meron din pagbabago sa voltahe from this point up to this point. So, maliit lang. Hindi siya halos makita. So pag meron tayong small changes in voltage or current, ang tawag doon ay dynamic resistance. Okay? Paano naman pag malalaki? No? Pag malalaki naman, we call that the average AC resistance. But you can use them interchangeably kasi pareho rin naman silang AC resistance. Okay? So pag maliliit, to be more specific, it's called dynamic resistance. Okay? So kung ipa-plot natin yung waveform ng voltahe, so i-zoom natin, ganito yung itsura niya. So magsisimula ka sa negative and then positive. So halos hindi na natin makita yung corresponding na sine wave based dun sa voltahe. No? So bakit ganyan? No? It may be that the current and the voltage are out of phase by 180 degrees. Okay? So this is the corresponding AC current, this is the corresponding AC voltage. So paano natin makukuha yung AC resistance? Yan ang tanong. Ohm's law pa rin yung gagamitin natin dyan. No, hindi magbabago. No? Always follow Ohm's law, but not applicable to some electronic devices, kagaya ng thyristors. So anyway, darating din tayo dyan pagdating sa electronics 3. Okay, so hopefully, umabot tayong lahat sa electronics 3. Okay, so what we're going to solve here is the AC resistance. So, tignan niyo ha, maglalagay ako dito ng small caps. Kanina yung ginamit ko, capital. Capital R kasi siya ay DC. But since this is AC, small letter R na yung gagamitin natin. So we name this as R sub T. So maliit yung, pati subscript niya maliit din kasi it represents an AC quantity. Okay? So how do we solve for RD? Ohm's law pa rin. Di ba kanina, volts over kuryente para makuha yung resistance? Ganon din naman dito. Volts over kuryente. Eh bakit capital? Bakit capital? Kasi we're taking the derivative, delta, for change. Don't worry, di tayo magde-derivative for now. Okay? You can think of delta as the change in diode voltage. Okay? Delta ID is the change in diode current. Okay? Paano natin makukuha? It's very simple. Delta VD. So let's say this is around 0.85. Teka, meron akong dito eh. Kasi sa buko ito kinuha, no? May specific value siya dito. Hindi ko kasi ma-project ng pag ganun. Sobrang liit. Ang given dito is point ano na to? 0.8 tsaka 0.78. Yun. Okay? So itong value na to, this is 0.8 volts. Itong value na to is 0.78. Hindi natin makikita yan no, unless talagang sinabi yung given. So 0.8 and 0.78. Ibig sabihin, naglalaro yung voltahe natin sa pagitan ng 0.78 at 0.8 volts. Kung ito yung ipa-plot natin, papalakihin natin siya. Let's say, ito yung voltage waveform natin. So nandirito ang value nito is 0.78. Ang value nito is 0.8. And this is your Q point. So dyan siya naglalaro. Okay? So delta VD, ibig sabihin niyan, change in VD. So highest value minus lowest value. So that's just equal to 0.8 volts minus ang lowest value niya, 0.78 volts. Divided by, ano yung change in ID natin? Anong value na ulit ka? So that is equal to from 20 to 30. So madali lang. That's 30 milliamperes minus 20 milliamperes. So this is equal to 0.02 volts divided by 10 milliamperes. So madali lang to kasi move one decimal place to the left. No, huwag nyo na i-calculator. So this is equal to 0.002. Anong unit? Volts per milliampere. Matik naka kilo ohms. But in terms of ohms, ilan siya? So 1, 2, 3. So this is 2 ohms. Okay? So this is the AC resistance. So bakit tayo nagkaroon ng AC resistance? Kasi ang in-apply nating waveform is AC. Ganun lang kasimple. But take note, no? The AC resistance is governed by Shockley's equation. So siguro mamaya ni Shockley's equation kasi meron siyang derivative na gagamitin. May differential calculus tayo. So I hope medyo nagbaon tayo konting calculus. Okay, what if ang input mo is still AC pa rin, pero sobrang laki? Unlike nito, no? Meron tayong delta ID, pero maliit lang yung change. At meron tayong corresponding na change sa VD, maliit lang. So we call that dynamic resistance, dynamic or AC resistance. Ito naman, ang tawag dito is average AC. Kapag sobrang laki ng voltage or current swing, kagaya nito, so sobrang laki, meron siyang malaking swing pagdating sa delta VD. It's also the same. So RAV, E, or the average AC, resistance is just equal to delta VD divided by delta ID, which is the same. Pareho lang naman. Kaya nga, they are both called AC resistances. But to be more specific, pag malaki, ang tawag sa kanya ay RAV, E, or average AC resistance. Ito naman ang tawag dito ay dynamic AC resistance. Okay? So, ganun din gagawin natin, delta VD. So, hindi ko na isosolve tong isa, no? Kasi alam niyo naman kung paano isolve. Highest value minus lowest value ng voltahe divided by highest value minus lowest value ng kuryente. Makukuha niyo yung average AC resistance. So, ito yung medyo madugo kasi yung sinasabi ko na Shockley's equation. Yan. May Shockley's equation. Hindi naman siya madugo talaga. Pero kung hindi kayo nag-aral ng differential, hindi niyo siya makukuha. Shockley's equation. Shockley's equation was developed by, papakita ko sa inyo kung sino yun. Nag-develop nito si, pupulak ko lang sa Google. Ito siya. Si William Bradford Shockley, isa sa mga bright minds, no, pagdating sa field ng electronics, napakalaki ng kanyang contribution. Kasi yung equation niya, meron din siyang Shockley's equation para sa mga field effect transistors or FET na tinatawag. Okay, so yan si William Bradford Shockley. So yung equation na yan ay siya yung nag-develop. So ano ba yung equation na yan? We're going to relate diode voltage and diode current. So we have the diode voltage I sub D is equal to I sub S, which is the reverse saturation current or the leakage current. So let me see kung may magpupulap ako ditong characteristic curve. Ay, sorry. Ano? What do you call this? Yung data sheet. At tignan natin kung makikita natin yung respective ano niyan. Reverse saturation curve. Okay, ito. Tignan natin kung meron nakalagay na reverse saturation curve. 1.4001. Ayan. Ay, hindi. Ano to? Reverse current to. Dito nakalagay yung I sub S. But anyway, hindi ko siya mahanap for now. Yung mga data sheet kasi ng mga different diodes, usually, nilalagay dito yung value ng reverse saturation current. So, ibig sabihin, itong Shockley's equation na to, hindi lang basta standard yung value ng I sub S. Pwede siya mag-iba-iba depende dun sa given na model ng diode. So, that's the reverse saturation current or leakage current. Depende sa model. Multiplied by E. Anong E? This is called Euler's number. Which is logarithm base 2.7. Okay? That's the natural logarithm or Euler's number na tinatawag. Or the exponential function na tinatawag. So, E raised to V sub D over N VT minus 1. This is in milliampere. So, this is Shockley's equation. Shockley's equation defines the characteristic curve. So, yung shape na nakikita nyo, yung parang curve na yan, pagdating sa forward bias region, tsaka pagdating din sa reverse bias region, is defined by Shockley's equation. No? So, pag pinlat natin yan, depende doon sa model ng diode na ginagamit natin, ganyan yung magiging itsura more or less. So, Shockley's equation defines the characteristic curve. But Shockley's equation can also be used to determine what we call the AC resistance R sub D. Okay, kasi important to dahil ang dynamic AC resistance is dependent on the DC current. Ulitin ko. The AC resistance or the dynamic AC resistance is dependent on the DC current. Bakit ganun? AC nakadepende kay DC? Balik tayo dito. Remember ito? Yan. Yan yung DC value, yung Q point. So what if meron tayong iba pang Q point na pinili? o pwede nang mag-iba yung value ng ating AC resistance. Okay, kaya nga nakadepende siya dun sa Q point, sa DC value. AC resistance is dependent on the DC value. In order for us to prove that, gagamitin natin ang Shockley's equation. Okay, so how do we do that? We will get the first derivative of the diode current with respect to the diode voltage. So, kukunin muna yung nating derivative ng kaliwang side. So, derivative of I sub t with respect to derivative of VT. Hindi yan dID divided by dVD. Hindi ganun It's properly stated as the derivative of ID with respect to the derivative of VT or V sub t. Yun ang proper na expression para dyan. So kung kukunin natin ang derivative ng I sub t sa left side ng equation, syempre kailangan din natin kunin ang derivative ng right side ng equation. So we have derivative of I sub s times e raised to vd over ndt minus 1. But before we continue, i-identify muna natin yung ibang parameters. Ano ba yung vd or v sub t? This is the DC diode voltage. So nakikita nyo na, no? Ang AC resistance natin, makukuha natin by using the DC value of current and DC value of voltage. Kasi nga, yung DC value of current at DC value of voltage defines what? Your Q point. Pares yan. So X is VD and the Y represents your ID. Ano yung N na maliit? N is what we call the ideality factor. Ideality factor, usually ginagawa ko lang 1 yan to simplify the analysis. In textbooks, they say that it's in between 1 and 2. So pwede natin assume na 1 to simplify our analysis. The ideality factor is dependent again on the diode na gagamitin natin. And it determines the shape of your characteristic curve. So kung pwede ba siyang papaganon, itsura, medyo palayo or medyo pa vertical, yung ideality factor ang nagde-determine nun. So it's safe to assume na 1. Okay? So in this case, pwede natin tanggalin na si N dito mamaya. V sub T is what we call the thermal induced voltage. VT is the thermal induced voltage or just simply stated as the thermal voltage. So ano ibig sabihin yan? This is the voltage developed in your semiconductor diode whenever there is a change in temperature. So pag nagbabago yung temperature natin, nakaka-apekto pala yan dun sa voltahe ng diode natin. And that is represented by the thermal voltage. The thermal voltage na yan, we have equals K times T over Q. Subset K. So sa connected, probably, I think nilagay ko to sa, kasi yung asynchronous natin, di ba meron tayong video na, may video lecture ako. Pagdating natin sa asynchronous part natin, I think meron akong lecture na diniscuss ko yan in detail. So dun yun na lang siya panoorin later on. So thermal voltage, K is Boltzmann's constant, which is equal to 1.38 times 10 raised to negative 23 joules per Kelvin. Q is 1.602 times 10 raised to negative 19 coulombs. And T sub K is the temperature in kelvins. But pahapyaw lang yan for now. Okay. So how do we get this value? So kukunin muna natin siya. I hope na alala niyo pa yung yung pagkuha ng mga derivative na yan. So kapag ang terms natin are separated by a plus or minus sign, anong gagawin natin? Kukunin natin ang derivative ng bawat isa. So derivative nito minus derivative nito. Actually, pwede natin silang i-distribute muna para mas maliwanag yung pagkukuha natin ng derivative. So I sub S times E raised to VD. Yung N pwede na natin tanggalin. Pwede natin i-assume as 1. That's why this is equal to VD over VT minus I sub S. So what I did here is dinistribute ko lang si I sub S dito tsaka dito. Okay. So para makuha natin derivative niyan, we will get the derivative of each term. So we have derivative of I sub S, E raised to VD over VT with respect to derivative of VT minus derivative of I sub S with respect to derivative of VT. So unahin natin itong I sub S. Since we are getting the derivative with respect to VT, ibig sabihin, lahat ng term na may VD, tatandaan nyo, lahat ng term na may VD are considered to be variables. Lahat ng walang VD or V sub T na term are considered as constants. So ibig sabihin yan, ito, yung second term natin, yung I sub S, may nakikita ba kayong VD sa kanya? Wala. Therefore, this is considered to be a constant. Ano ang derivative ng isang constant? Diba that is equal to 0? Bakit? Bakit ang derivative ng constant ay 0? Remember, ang derivative can be also expressed in terms of delta. So pareho lang ibig sabihin niyan. This represents change. Ang constant ba nag-change? Hindi. That's why kapag kinuha natin ang change ng constant, that is equal to 0. Okay? So kaya ang derivative ng constant ay 0. Wala namang pagbabago ang constant. Diba? Derivative denotes change. O, dito tayo magpo-focus ngayon sa pangalawa. So we have I sub S, E raised to VD over VT. So itong term na to, may kasama siyang VD. Therefore, hindi magsisiro ang kanyang derivative dahil meron siyang variable na kasama. But since I sub S is considered to be a constant, matik labas na agad yan. So this is equal to, labas agad si I sub S, derivative of E raised to VD over VT with respect to the VT. Okay? So, this is equal to, anong derivative ng E raised to U? Kung naalala nyo, derivative of E raised to U. This is equal to E raised to U du. But in this case, ano yung nagsisilbing U? So, focus ha. Yung U, yan yung exponent ng E. Ano yung exponent niya? VD over VT. So, isusulat natin dito. So, medyo i-center lang natin ang content yan. So, VD over VT. So this is also equal to 1 over VT times VT. Okay? So 1 over VT is a constant, VD is a variable. So what is the derivative of U? Derivative of U with respect to dVT, or dVT2, derivative of VD, that is now equal to 1 over VT times derivative of VD with respect to derivative of VT. So magka-cancel out siya. Magiging 1. Anong matitira? 1 over VT. Okay? So salpak natin sa kabila. Kailangan daw makumpleto ito. Makumpleto itong derivative ha. E raised to U. Okay, sulat muna natin si E raised to U. E raised to U. Ano daw yung DU? Ang DU natin is 1 over VT. So times 1 over VT. Pero meron pa tayong kulang doon yung IS. Okay, we can simplify this one. This is I sub S times E raised to VD over VT over VT. Oops. VD over VT. This is equal to the derivative of ID with respect to derivative of VT. Pero hindi pa dyan nagtatapos. Okay? Ang gusto natin makuha is yung, ano ba kinukuha natin dito? Bakit natin kinuha yung derivative ng kuryente na yan with respect to VT? Gusto natin makuha yung AC resistance. Ha? Paano AC resistance dyan? Mamaya makikita nyo. So tuloy lang natin. Ha? So I want you to focus on the numerator of the right-hand side. Yan ha? Yan. So I sub S, E, VD over VT. Okay. Remember our original equation for Shockley's equation? Original form, I sub D is equal to I sub S times E raised to VT over VT. So tinanggal ko na yung N, equal to 1 ko na lang siya to simplify, minus 1. So this is original Shockley's equation. If I'm going to distribute IS, this is IS, E raised to VD over VT minus IS. So, dinistribute ko lang. Naging ganito na siya. Okay? So, next. Hahanap tayo ngayon dito. Mayroon bang kamukha ito? Itong bibilugan ko yan dito sa equation na nasa baba. Yes. So, ito, kamukha nung nandito. Tatanggalin lang natin yung VT. Okay? So, paano natin makukuha yun? So, we can rearrange this equation into ID. Transpose natin sa left side yung IS. Magiging positive na siya. Okay? This is equal to IS E raised to VT over V sub T. So, kamukha na siya ngayon nitong nasa taas. Meron lang over VT. So, we can further replace this one, okay, with this. Okay? So, this is ID plus I sub S over VT. Itong nasa taas, ni-replace natin yan, naging ganito siya, galing dito sa baba. Okay? So, next. Gawin natin pula. Okay. Ano may gagawin natin dyan? So, i-rewrite natin siya dito. No? We have derivative of ID with respect to derivative of VD is equal to I sub D plus I sub S over VT. Okay. Na-reduce na natin yung Shockley's equation into this one. Na-reduce pa yung lagay na yun. No? So, how do we further simplify this one? Kasi ang aim talaga natin dito, makuha yung AC resistance. Mamaya makikita yung AC resistance na yun. Okay, mag-alala. ID and IS. ID is the diode current kapag naka-forward bias. Remember, ang level nito, alin? Anong level nito? Nasa milliamperes. Anong level ng I sub S? Nasa nano or picoamperes. So, ibig sabihin, I sub D is much greater compared sa I sub S. It's like adding 1 million plus 10. Okay? Parang ganun. So, 1 million plus 10 is equal to 1 million and 10. So, yung 1 million and 10 na yun, this can be simplified as 1 million, di ba? So, therefore, since ito yung ating condition, maliit talaga yung value ng leakage current na yan, kumpara sa diode current natin kapag naka-forward bias. That's why we can eliminate I sub S. So this is approximately equal to I sub D over VT. Hindi pa dyan nagtatapos ulit. Kasi nga, AC resistance yung kinukuha natin eh. AC resistance ng diode. No? So we have derivative of ID with respect to dVT equals ID over VT. Okay, remember, AC resistance, R sub T, is equal to delta VT with respect to delta IT. Okay, itong equation natin, derivative of ID with respect to delta VT, baliktad. Kung kukumpara mo itong dalawang to, tsaka to, baliktad. Ano gagawin natin? Di baliktarin mo rin to. Baliktarin natin para makuha mo si AC resistance. So kung babaliktarin natin siya, we have dVd with respect to dId is equal to V sub T over I sub T. Or the AC resistance R sub D is equal to the thermal voltage divided by the diode current. So this proves na ang AC resistance ay nakadepende sa DC na kuryente. Okay? So this is how we solve for the AC dynamic resistance. Ang V sub T, may standard value yan actually na 26 millivolts. Ang derivation yan, I think nandun sa video ko. Isasend ko na yung link sa inyo pagdating natin sa topic na yun. So hindi ko muna siya isasend ngayon para hindi halo-halo. Okay, so this is the governing equation to get the AC dynamic resistance. Okay, so I know medyo malabo sa inyo to ngayon kasi sobrang dami ng kinumpute natin. Diba? So I'll try to print this out later on. And then isasend ko sa inyo. Na-print ko na siya one time sa isang klase ko, then sinend ko. I'll try to print it out mamaya. Dun sa, as PDF ata yun or as JPEG. So anyway, so habang check muna natin attendance before we go to wave shaping circuits. Masarap talaga mag-ECE yan. Okay, attendance muna tayo. Okay, attendance. So by the way, no, habang tinatype ko itong attendance natin, baka nabalitaan nyo na, no, may announcement si Secretary Popoy De Vera ng CHED na may panukala na ibalik na ang face-to-face classes, no, for nasama yung engineering technology. Mamaya papakita ko sa inyo para para some sort of parang pahinga kahit paano dito sana before tayo mag-proceed. So that is our first attendance. Ito yung napapakita ko sa inyo muna. Para medyo pahinga muna yung kahit paano dito sa ano lang natin na some tidbits. Kahit tanungin ko kayo, may question ba? Sabihin nyo, pakiulit. So, isa-send ko yung ano sa inyo to. Subok kong i-print namin. Ito yung post ni Popoy De Vera. Yan. So, kasama ang engineering and technology programs sa papayagan na makapag face-to-face. So, maganda rin malaman nyo na to kasi pagdating ng time na i-approve yan, wala pang no. Tinanong ko rin yung CHED Region 3, sabi nila itutuloy daw talaga yan, yung face-to-face. Pero, ang nag-meeting kami kanina, sabi, ang napag-usapan namin is yung mga laboratory classes, yun lang yung mag-on-site. And then yung mga lecture, online pa rin. Kasi para malimitahan pa rin yung mga pupunta sa school. So anyway, yung ibang programs naman, kagaya ng psychology, ng management, hindi pa sila mag-on-site, hindi pa sila mag-face-to-face. Kasi hesitant pa kami dahil hindi pa naman lahat kayo nabakunahan. Although may iba nang nabakunahan, hindi lahat. So mapuput into risk. Kaya posible tayong magkaroon ng laboratory classes kay Sir Chris Sapihon. No? Posible lang itong semester na to. Baka lang kasi kasama doon sa engineering and technology programs yung sinabi ng CHED. So September 21, in-approve na yung authority na yun for face-to-face activities. Ang dayunin kasi nito is magkaroon ng face-to-face classes yung mga kailangan ng hands-on. So kailangan ng hands-on yung laboratory. Yung lecture, hindi naman kailangan ng hands-on yan. So most probably. And iniisip din kasi namin yung kaligtasan din ng mga faculty members and yung mga estudyante. No? But in line with this, magpapasurvey ako sa mga officers about siguro yung kung payag ba o willing ba or hindi. Yung mga estudyante na magkaroon ng face-to-face laboratory classes at kasama din yung magulang. So, kung papayag pa sila. And titignan din namin kung nabakunahan na syempre. Kasi hindi ko man nabakunahan na hindi pwedeng mahawa. Pwede pa rin mahawa pero mild na lang, di ba? Sabi ng news. So ako, hindi ako nangangamba sa sarili ko, pero sa family ko nangangamba ako pag nag-face-to-face classes tayo. Kasi syempre, meron akong bata, 6 years old. No? Yung asawa ko, tsaka ako, bakunado na kami, fully vaccinated na. But yung anak namin is hindi pa. So ganun din, I think yung iniisip din ng ibang faculty members na syempre may mga pamilya sila. Kayo din, no? Mga bata pa, hopefully, mabakunahan na rin kayo kasi in-approve na, di ba? Yung 12 to 17. Ay, hindi na kayo 17, yung mga matatanda na kayo, di ba? So, I hope na mabakunahan na rin kayo. Okay, so balik tayo sa klase. Anyway, okay, so yun yung sinasabi ko sa inyo na ang diode can have different resistance levels. So pwede tayo magkaroon ng DC, kung in-apply natin ay DC voltage, pwede din tayo magkaroon ng AC na resistance or impedance kapag ang in-apply natin ay AC naman na voltahe. It's proper that we address this resistance as impedance. So dapat natin siyang tawagin impedance para masanay na tayo sa term na yun. Kasi pagdating sa communications, yung impedance na term, ginagamit din natin yan. Okay? Tama rin naman natin sabihin na impedance siya kasi resistance is also impedance. Okay? So punta na tayo ngayon sa first application ng semiconductor diode. So hindi ko pwedeng palagpasin talaga tong diode ng ng wala ito, yung mga yan. No? Hindi pwedeng mag-proceed tayo agad sa wave shaping circuits ng wala yan. So yung iba sa ibang klase I experienced before. Rekta agad sa wave shaping circuits without explaining itong mga bagay na to. So I hope kahit paano, no, at least na-expose kayo dito sa mga concepts na to. Okay. So the first one, so punta tayo sa wave shaping circuits, no? Wave shaping circuits. So ibig sabihin yan, sinishape niya, hinuhugisan niya yung wave natin. So ang first wave shaping circuit natin yung tinatawag na rectifier. Oops, rectifier. Rectifier, we have two types. We have the half-wave rectifier and we have the full-wave rectifier. So probably ang madidiscuss ko lang now since medyo mag-4 na rin. Yung half-wave rectifier muna. So we have half-wave rectifier. Ano ba yung rectifier na yan? Rectifier converts AC to pulsating DC. Ulitin ko, no? Rectifier converts AC waveforms to pulsating DC. Bakit tinawag na pulsating yan? Kasi may parang pulso siya. So later on, malalaman natin. For this discussion, ipapakita ko sa inyo yung model ng diode kapag siya ay ideal and if it is practical. And then papakita ko sa inyo later on yung tinatawag na piecewise linear tsaka yung simplified equivalent circuit ng diode. So half-wave rectifier muna tayo. Ang half-wave rectifier is composed of only one diode and we can use here one resistor. Okay? This is the basic circuit for a half-wave rectifier, but it is not always a resistance. Take note. This can be any load. Pwede yan ay maging regulator na, pwede maging capacitor, so on and so forth. But in textbooks kasi, no, kapag dinidiscuss ang half-wave or rectifiers in general, gumagamit tayo ng resistive na load to simplify the discussion. So this will represent your load, R sub L. Okay? So ang load natin, dyan natin kinukuha yung output voltage. So ang output voltage natin, plus minus V sub O. Okay? So ibig sabihin, kung meron tayong tester o kung meron tayong oscilloscope, hindi ko alam kung na-present na sa inyo oscilloscope. No? Kasi kung meron na oscilloscope dito. This is your oscilloscope. Teka lang. Okay, so oscilloscope natin. Oscilloscope kasi is a device. Ulit ako ng image na lang sa Google. Oscilloscope. So kung hindi pa na ipakita to, if ever lang. So ito yung tsura ng oscilloscope, more likely. Meron tayong screen, meron tayong mga different control buttons and knobs. Basically, ang trabaho ng oscilloscope is to display voltage waveforms. It cannot display current waveforms. Okay, tatandaan yan. So, kung ano yung itsura niya, for example, yan, may AC, pwede natin display. DC, pwede rin natin display dyan. Pwede niyang i-measure yung frequency, yung phase. Yan, meron tayong square wave, may triangular wave, so on and so forth. Any voltage waveforms, pwede natin i-display sa oscilloscope. Okay. Sa oscilloscope, usually meron tayong two channels. So, for example, yung isang channel, channel 1, dinedicate natin for the input, yung isa dinedicate natin for the output. For us to be able to connect the oscilloscope sa ating circuit, gumagamit tayo nito. Hindi ko alam kung nakikita nyo. Paano ba yung view nito? Makita yung view. So I think nakikita naman, no? So ito yung oscilloscope probe na tinatawag. Oscilloscope probe, think of it as the test leads ng mga tester natin. Di ba yung test lead natin may positive at negative, may pula at itim. So kapag binaliktad natin yan, magiging negative yung measured voltage natin, di ba? So ito yung probe. This is used to interface the oscilloscope to your circuit. Itong clip na to, it represents the negative. Itong clip. Itong hinahatak natin, yung hook, hindi ko lang kung nakikita niya, may hook. This represents the positive. So this is the positive, this is the negative. Lalagay mo siya usually sa ground. Ito ilalagay mo dun sa test point na tinatawag or TP. Ay, nabalik ko ata. Balik ko na. Okay. Yan. So pwede itong hatakin yung takip. Yan. So pwede mo itusok dun sa test point. Okay. Pwede rin naman ganito, i-clip mo doon or i-hook mo doon sa certain test point na yan. So this is positive, this is negative. Okay, balik tayo dun sa kanina. Yung positive na yan, this represents the hook of the oscilloscope. Yung negative na yan, that represents the clip of the oscilloscope probe. So tatandaan nyo. So yan yung gagawin nating orientation for the to get the output. Okay. So, for example, we have one diode. Let's say this is ideal. We'll analyze the circuit first using an ideal diode. So, ang ideal diode kapag forward bias, matic. Pag positive ang anode, forward bias siya agad. So, di ba, napakasimple, no? Ng analogy natin kapag gagamit ang ideal diode. So, para lang mapabilis yung analogy natin. Kapag negative ang anode, ang equivalent niya ay open circuit or reverse bias. Okay? Usually, yung mga rectifiers natin are connected to a transformer. Hindi na naman ako nakapagdala ng transformer. So anyway, next time. Usually, meron tayong, for example, step-down transformer. Ganyan. Let's say 10:1. Halimbawa. So kung 220 to, input natin dito sa primary. Alala niyo pa yan, yung primary winding. So this is the primary voltage, V prime. So ano magiging secondary voltage natin? Kung 10:1 ang ratio. So 10 parts nito, 1 part lang nito. So basically 220/10. So ang secondary voltage natin, RMS, is roughly around 22 volts. Okay? Kasi yan yung ratio natin, 10:1. So 10 parts sa primary, 1 part sa secondary. So kino-connect natin yan sa rectifier. Ang input mo dito is AC. Ang output mo dito sa secondary is also AC. Pero mas mababa yung amplitude. Okay? But the question here is, ano ang peak voltage niya? Okay. Ang kuryente natin sa saksakan, sa mga power outlets natin, are in the form of sine waves. Sine wave yan kapag dinisplay mo sa oscilloscope. Hindi ko na siya pinapadisplay sa oscilloscope usually pagdating sa laboratory. Kasi mataas yung risk na pwedeng meron magkamali, makuryente. No? Kaya, ang ginagawa ko, ako na lang nagde-demonstrate usually sa kinoconnect ko. But hindi ko na rin demonstrate lately kasi there was this oscilloscope na nasira. So hindi pala niya kaya yung 220 volts. So nasira. So sayang yung oscilloscope. But I can tell you that the shape of the power na lumalabas sa ating outlets is a sine wave. Sine wave ang lumalabas dyan. Okay? So, we have to determine first the peak voltage. Sa secondary tayo nakafocus kasi ang rectifier natin naka-connect sa secondary winding natin. Okay. So, let us get first the peak voltage. Anong formula natin to determine RMS or to relate RMS and peak voltage? We have VRMS or the root mean square is equal to peak voltage divided by square root of 2. Yan given natin na RMS. So makukuha natin yung peak voltage, that is equal to square root of 2 times VRMS. So that is equal to square root of 2 times 22 volts. Calculator dito na lang sa Windows. Okay. Square root of ay, balik tayo. Huwag na pala yung number 2. Square root. Yan. Times 92 equals 31 volts peak. Okay. 31 point something. 0.11. So, this is your peak voltage sa positive half cycle. Sa negative half cycle naman, it's negative 31.11 volts peak. Ang peak to peak natin is just twice the value of this one. So roughly around, let's say, 62.22 volts peak to peak. Okay? But to simplify our analogy, mag-a-assign na lang ako ng peak value. So let's say 10 volts sa positive half cycle and negative 10 volts sa negative half cycle. Okay? So we're going to analyze first sa positive half cycle. So positive half cycle muna tayo. Usually ang ginagawa ko sa klase, nilalagay ko lang plus HC. Ibig sabihin yan, positive half cycle. Okay? So for the positive half cycle, dodrawing ko muna dito yung aking half-wave rectifier. So remember, ang half-wave rectifier, isang diode lang, pointing to the right. Pwede rin namang pointing to the left. Okay? So this one is pointing to the right, and this is your output voltage measured from this one. Nandito yung positive or yung tip ng probe natin. Nandito yung negative. This is the output voltage. So sa positive half cycle, papasok ito. Okay? And ang peak niya is 10 volts. Ibig sabihin, yung nasa taas is positive, yung nasa baba is negative. This is for the positive half cycle. Okay? Kasi di ba, dito pumapasok sa taas. Okay. Next. We're going to determine the state of the diode. If it is forward or reverse bias. Tignan natin si anode. Si anode sa nakatapat, doon kay positive. Si cathode sa nakatapat, doon kay negative. So ibig sabihin, si anode is positive and cathode is negative. Remember, this is an ideal diode. Sabi ko sa inyo, kapag ideal ang diode, matic. Matic forward bias yan kapag ang anode ay positive with respect to the cathode or ang cathode is negative with respect to the anode. Ano ang equivalent niya kapag naka-forward bias? Iba, ang equivalent niya kapag naka-forward bias is ito. It's equivalent to a short circuit. No? Yan ay for the ideal diode. So, tayo dito. Palaki ng palaki sulat ko. Okay. So let us now redraw our circuit during the positive half cycle. So this is the equivalent circuit. So instead of the diode, i-replace natin siya ng isang short circuit or ng isang closed switch. Di ba kanina diode siya? Ngayon, closed switch na siya kasi yun ang equivalent niya kapag naka-forward bias. Okay. So we have here this one, plus, minus, peak, 10 volts. And then we have plus, minus, PR. Okay? So what is your output voltage? The output voltage is measured across R sub L. Eh kung mapapansin niyo R sub L, rekta siya doon sa input. Nakaparallel siya doon sa input. Therefore, kung anong pumasok, yun din ang lalabas. So what is the output voltage? The output voltage during the positive half cycle is equal to 10 volts peak. Or the output, the output is equal to the input. Yung O over P, ibig sabihin yung output. Yung I over P, ibig sabihin yung input. Ha? Okay. That is for the positive half cycle. Ang pumasok, positive half cycle. Ang lumabas, positive half cycle din na mayroong peak voltage na 10 volts. Okay, next. Of course, mag-analyze naman tayo sa negative half cycle. So for the negative half cycle, okay, So this is the circuit. Half-wave rectifier, isang diode palagi yan. Half-wave, isang diode. Tatandaan nyo, isang diode. Ang dami kong estudyante before. Pagdating ng 5th year, construct nyo ito ng half-wave rectifier. Napakasimple. Hindi nila matulungin. Hindi naman lahat. Tapos nag-mock ako sila sa kanila ng mock board exam ako sa kanila. Isang question doon, galing sa actual na board exam. How many diodes does a half-wave rectifier have? Baba, ang daming hindi nakasagot. Hindi nakikinig sa akin ng electronics 1, 2. Isang diode lang ang half-wave rectifier. Tatandaan niyo yan. Okay? So next. So dito na tayo sa negative half cycle. Kanina, positive yung taas, negative yung baba sa positive half cycle. Sa negative half cycle, mababaliktad yung polarity. Negative yung taas, positive yung sa baba. Therefore, meron tayong ganitong waveform. So this is negative 10 volts peak. Okay? So output voltage natin is still measured in this manner. Okay? Nandito pa rin yung positive, nandito yung negative. Okay. Ano kayang kondisyon ng diode natin? Okay. So tingnan natin, no? Yung anode, nakakonect kay negative. Si cathode, naka-orient kay positive. So negative ang anode, positive ang cathode. This is reverse bias. Okay, yung kanina, this is forward bias. So sabi, ano daw ang equivalent circuit ng diode kapag naka-reverse bias? So balik natin sa kanina para sa benefit ng lahat. Kapag naka-reverse bias daw yung diode natin, it's equivalent to an open circuit or open switch. So papalitan natin ng ganito yung circuit natin, no? Equivalent. So this is the equivalent circuit. So equivalent circuit, So i-redraw natin siya, pero this time open circuit na siya. Pwede natin alisin na yung line na papagan. Pareho lang naman ito sa ganito. Okay? So tanggalin na natin to simplify our diagram. Pareho lang namang open circuit yan. Okay. Next. Wait. So, lagay pa rin natin yung load. Di pa rin makawala yung load dyan. And then we have rewrite again the inputs minus 10 volts peak and plus minus P out. So in this case, it's an open circuit. Ang open circuit, walang dumadaan na kuryente. Hindi nakakadaan yung kuryente. No? But in reality, di ba, ang diode, merong dumadaan na kuryente kapag naka-reverse bias. But it's very, very small. That's why it's considered to be zero. That's why ang equivalent niya ay open circuit. Kasi sa open circuit, zero ang kuryente. Walang dumadaan na kuryente whatsoever. Okay? So, what will be the output voltage? Remember, meron tayong RL. Kanina, nung forward bias siya, may daanan ng kuryente. May kuryente, may resistance, may voltahe. Ohm's law. May kuryente, may resistance, may voltahe. Dito, may kuryente ka ba? Wala. Walang kuryente, may resistance ka. Meron ka bang voltahe? So let's prove that using Ohm's law. V out is equal to I. So ito yung kuryente natin, no, from positive to negative. Kuryente is equal to 0. I times RL. Eh 0 yung kuryente mo kasi nga open circuit. So 0 milliamperes times RL, any value of RL is still equal to 0 volts. So ang output mo during the negative half cycle is equal to 0 volts. So during the positive cycle, ang output mo is equal to 10 volts peak or the output is equal to input. But during the negative half cycle, the output is 0 volts. This is for the half-wave rectifier. Eh what if umulit naman? Kasi di ba this is an oscillation. Oscillation meaning periodic and umuulit. So uulit-ulit sa positive half cycle. Ano magiging output mo sa pangalawang positive half cycle? E di ganun ulit. Umulit yung negative half cycle. Ano magiging output mo? E di ganun ulit. So ulit-ulit lang yan. 10-0, 10-0, 10-0. Okay? So let's plot it. Input versus the output. So this is your input. Ito yung ating input voltage. V sub I, represented by V sub I, and this is x-axis is time. Pwede rin natin gawin yan in terms of theta or yung phase, yung angle. No? So this is your input. So positive half cycle, negative half cycle. Medyo okay drawing ko ngayon. So 10 volts, this is negative 10 volts. This is plus HC for the positive half cycle. Medyo i-zoom natin na kasi parang malabo ata. And this is the negative half cycle. Okay. I-project natin yung pababa. What is the corresponding output voltage waveform for each half cycle? So drawing natin. So y-axis now represents V out. No? Kasi ito yung V in natin. And V out represents the output voltage. So we have the x-axis should also represent the time. So kung ginamit mo sa input ay time, dapat yung x-axis mo sa output, time din. Okay? Represented by E. So during the positive half cycle, ano daw yung output natin? Positive 10 volts. Or kung ano yung pumasok, yun din yung lalabas. So ito yung pumasok ito yung nasa taas. Highlighter yan. Ito yung pumasok natin. So dapat yan din yung lalabas. So lalabas natin, kamukha din dapat ng input. So this is 10 volts. This is during the positive half cycle. Okay? During the negative half cycle, ano daw yung output natin? Zero. Nag-zero yung output natin, nag-0 volts. So 0 volts represents a flat line. So flat line lang yan. Okay? This is for the negative half cycle. Eh what if uulit? Cycle na yun, no? Meron tayong oscillation. So ulit-ulit yung positive half cycle, ulit yung negative half cycle, so on and so forth. So it will still be equal to this one. Pagdating na negative half cycle, flat ulit. So 10 volts, 0 volts, 0 volts. Anong napapansin yung direction ng voltahe natin? Puro positive lang all throughout, di ba? This is DC. Isa lang ang direction ng current or yung direction mismo. Okay, puro positive lang. Pero, mapapansin natin, hindi siya purong DC. Kasi ang purong DC, ganito yung tsura. Dire-diretso lang. Mapapansin natin may mga kurba. So this is what we call pulsating DC. May pulses ka. So, to be more specific, this is a half-wave rectified signal. Okay, ang objective natin is to have pure DC. Paano tayo magkakaroon ng pure DC? By using capacitors. Okay, the capacitors are used to smooth out our output. Okay, but in half-wave rectifiers, hindi tayo gumagamit ng ng capacitors. Sa full wave lang tayo gumagamit. Kasi ang mangyayari niyan, pag dinaretsyo natin, ganito magiging, pag dinaan natin siya sa isang capacitor, more likely magiging itsurang square wave na siya. Okay? So, which is undesirable kasi ang square wave, it introduces harmonics. Anyway, pagdating natin sa communications, malalaman natin harmonics na. Okay. So, this is a half-wave rectified signal. Nakikita nyo, di ba, meron siyang mga kurba. Ang tawag doon sa kurba na yun, or I'd like to call it latak, those are called ripples. Ripples are the amount of AC in a pulsating DC. Latak kasi. Bakit latak? Kasi siya yung natira ng AC. Dapat pure DC na yun, di ba? So yan yung latak. Okay, ripples. So this is a half-wave rectified signal. So we have converted the AC into DC. Pulsating na lang. Yun ang disadvantage ng half-wave rectifier. Kasi kalahati lang ng waveform natin ang na-utilize or nagagamit. Wherein sa full-wave rectifier, yung entire waveform natin ay nagagamit. No? So next meeting natin, i-discuss ko sa inyo how do we get the average value or the DC value ng isang rectified signal? Kasi gusto natin makuha the most out of the output DC. Ilang DC ba makukuha natin dyan? Kukompute natin yun using integral naman. Integral calculus. Magbaon-baon kayo ng integral calculus next time. And also, i-discuss ko rin yung diode models natin. No? Yung piecewise linear, simplified equivalent circuit. Okay, so yung dalawang model niya. So I'll try to print this out and i-send ko dun sa GC natin. But lastly, ano muna tayo? Attendance for transparency. Ayan. So 1, 2, 3, 4, 5, 6, 7. So present naman na. Okay. So I'll just see you on Friday. Okay, bye.